Question number 8. Calculate moment of inertia of a rod along z-axis if the linear mass density changes according to equation lambda is equal to a plus bx. Small mass dm, and dm is located at distance of r, and small length will be dr. I think it is better to use x. I think so. Yes. If you use x is better. X, this is dx because it is along x-axis clearly given. So first of all, we use the logic of linear mass density lambda. Lambda is equal to dm by dx. That is equal to, lambda is given already, a plus bx, right? A plus bx. Good. Now, I can write like this. That implies dm is equal to a plus bx into dx. Next thing, we know the formula for moment of inertia I. I is equal to integral r square dm. In this case, r square will become x square. That is equal to integral x square. Dm value directly, I'll put it from here, okay? Dm is equal to a plus bx. I think a, b values are being given. We can put those values. So it will be integral a x square dx plus integral b x cube dx. If I integrate a x square, a is constant, so it will be x cube by 3 plus into a b x power 4 by 4, right? Yeah, you have to integrate these things between the limits 0 to L. No need to discuss much. When you put 0, it will be 0 only. So I'll substitute the value of a also. A is 6. 6L cube by 3 plus b is 4. 4L power 4 by 4. When you cancel 2 times. So answer for moment of inertia I is equal to 2L cube plus L power 4. Solve question number 9. Now let us take an axis, then rod, and its mass is m. It's making an angle theta with the axis. Okay, right. Now standard stuff, we need to take small mass dm. I took small mass dm, and it is at a distance of x. You can take, no problem. And then length is dx. I use linear mass density lambda. Total mass by total length is equal to small mass dm by small length dx. That implies dm is equal to capital M by L into dx. Moment of inertia I is equal to integral r square dm, where r is perpendicular distance. Observe here, x is not the perpendicular distance. Perpendicular distance means this distance, right? Anyone is there who can tell me how to calculate that perpendicular distance? Zoom in. Yes. This distance. How to get it? The distance is not x. X sine theta. Check it. So r is equal to x sine theta. That implies I is equal to x square sine square theta dm integration. Just a minute. I need to take d capital M. Now put the dm value here. X square sine square theta into capital M by L into dx integration. Now sine square theta is constant because throughout the rod angle is theta only, na? So capital M by L sine square theta will come out, integral x square dx. X value changes from minus L by 2 to plus L by 2. So if you solve it, M by L sine square theta x cube by 3 limits L by 2 to L by 2. But this is positive, this is negative. So if you apply limits, then M by L sine square theta, okay, 1 by 3 I take it out, into L by 2 whole cube. L cube by 8 minus L by 2. It will be minus or minus plus L cube by 8. Now it will be I is equal to M L square sine square theta by 12. After this, again, you have to cross check the boundaries. Once you got the answer, you must cross check if at all possible. Okay. What is the cross checking? See, you know very well a rod will have moment of inertia ml square by 12 about an axis which is perpendicular to the plane, right? We already did it. ml square by 12, and you will memorize it. You have to memorize and you will memorize it. So use that one. If theta is equal to 90, it should match with that value, ml square by 12, perfectly matching. And theta equal to 0. When theta is equal to 0, rod is like this. When rod is like this, all the particles of the rod are on the axis only. When every particle of the body is on the axis, perpendicular distance of all the particles are 0, moment of inertia 0. So put theta 0, moment of inertia 0, perfectly matching. This method will eliminate errors. Question number 10. Let us take the semicircular ring like this. Now, how to calculate moment of inertia? Small segment I take, its mass is dm. That makes small angle d theta, a very small angle d theta, and angle made with y-axis. Y-axis is theta. Small length dl we take. That dl must be equal to r d theta. I think you know this. Right. Now, we need to know perpendicular distance from the y-axis. Or x also we can take. I'm calculating first iy. From the y-axis, this one, r sine theta, right? Moment of inertia of the small piece about y-axis will be mr square. M is dm. dm into what is r? R square sine square theta. Right? Total moment of inertia I will be equal to integral r square sine square theta dm, right? Good. Now what to do? Link between dm and theta is required because both are variables. R is a constant. So total mass by total length is pi r. That must be equal to small mass dm r d theta. Now r gets cancelled. That implies dm is equal to m by pi d theta, right? M by pi d theta. So if I substitute that value here, that is equal to r square will come out integral sine square theta. Dm is what? M by pi d theta. If I take m by pi out, mr square by pi integral sine square theta d theta. Now we can't integrate sine square theta. What we do is that we take an identity 1 minus cos 2 theta by 2 is equal to sine square theta. We use this identity. So I replace sine square theta with 1 minus cos 2 theta by 2 mr square by 2 pi. What I did is that this 2 is there, na? I took it common. Directly I'm writing integral 1 minus cos 2 theta d theta. Now you need to integrate mr square by 2 pi. Integral 1 d theta is theta. Limits 0 to pi. That's the biggest problem. Student will take it like this. Point is, you need to understand, if you take theta with x-axis, then the limits will be 0 to pi. But you took it with y-axis. So The limits will be minus pi by 2 to plus pi by 2. Can you understand? So when you're taking limits, you should not take blindly. A little bit careful. Minus cos 2 theta. Integration of minus cos theta will be sine 2 theta by 2. Again, the limits are same. Minus pi by 2 to plus pi by 2. Right? Oh, I need to put a bracket. Yeah. Everything under bracket, right? Good. That is equal to mr square by 2 pi into pi by 2 minus or minus plus. Okay, right. Pi by 2 minus or minus plus pi by 2 is the value. Now this will be 0 because sine 2 into pi by 2. Sine pi, 0. Again, sine 2 into minus pi by 2. Again, sine minus pi. Whatever it is, 0. That is equal to mr square. This will be pi. The total value will be pi. This value is pi. And that pi and this pi gets cancelled. Pi gets cancelled. Then it will be mr square by 2. I did it about y-axis. You can do it with x-axis also by simply replacing sine square theta with cos square theta. Observe, perpendicular distance from x-axis what? R cos theta, na? That's why. Now we did integration for few objects, but in the world there are many different types. Standard shapes itself, shell, sphere, many are there. So what we do is we will remember some standard objects like ring, disc and all, and we memorize and we develop on it. First of all, let us consider first this thing that axis passing through center and perpendicular plane. If it is a two-dimensional object, our focus is on the axis which is passing through center and perpendicular plane. If it is three-dimensional object, it's very simple, passing through center, that's it, okay? Let us take the very important thing, that is first one is ring. Ring case, as I told you, the ring is there like this and the axis is passing through the center of the ring and perpendicular plane. Moment of inertia mr square. Okay, next disc. Disc diagram wise looks same. Okay, mr square by 2. Rectangular plate. Rectangular plate means there is a plate whose length and breadth is A and B, and there is an axis passing through the center of the plate and perpendicular to the plane of the plate. Okay, and remember, all the objects are uniformly dense. Okay, right. Moment of inertia will be ma square plus b square by 12. Rod will be ml square by 12. I think so. Yeah, ml square by 12. Rod will be ml square by 12. Next one. Sphere. Solid sphere will have moment of inertia 2 by 5 mr square. Shell will have moment of inertia 2 by 3 mr square. This is what you need to know, nothing else. So what is my recommendation is that just mug up ring, disc, rectangular plate, rod, solid sphere, shell. Okay, I repeat, ring, disc, rectangular plate, rod, solid sphere and shell. These are things we need to remember. Once you remember this, we can develop it further. Sir, how can? Concentrate here. First of all, we have the moment of inertia of a particle. From the particle, we go to objects, right? You know how to integrate. Sir, we do integration. No. We will try to bypass integration by either using table. Table is there, na? We try our level best to use the table to minimize what? Integration process. And then we use theorems to solve about other axes because this table will give you moment of inertia of a sphere about center. Fine. But if the question is all about moment of inertia about the tangent, then you can't remember for everything, na? Bit more difficult, right? So what is my point is that to deal with known objects with a different axis, then we use theorems. There are two theorems. Then after that, there is a thing called as sense. Some sense will be there. By sense also you can pick up. Last thing, nonsense. What is nonsense? I'll tell you. First, let us understand the theorems. Okay. There are two theorems in moment of inertia. Parallel axis theorem. Let us consider an object. It can be any arbitrary shape. And center of mass is here assumed. And we know moment of inertia about center of mass. We know that. ICM we know. Now we want to find moment of inertia about any other parallel axis. Okay. The distance between them is d. how to calculate the moment of inertia about this parallel axis if you know moment of inertia about center of mass, or vice versa also true. That is I is equal to ICM plus MD square. What is M? Mass of the object. What is D? The perpendicular distance. Okay. Last class, we did a problem where moment of inertia of the object is minimum about center of mass. We got that, right? By observing this theorem, also, you can find the same statement. Moment of inertia about any axis is equal to moment of inertia about center of mass plus something. Sir, mass cannot be negative. No. D may be negative, but D square will be positive. So this is always positive value. So moment of inertia about any axis is moment of inertia about center of mass plus something. Means what? Moment of inertia center of mass is minimum. I can indirectly tell that. Anyway, let us continue with the rules. The rule says it can be used for 3D objects also. Sir, why? Why you are giving this statement? Actually, next theorem is applicable only for 2D objects like planar objects. So that will affect here. That's why I'm giving it to you. You can use it for 3D objects, sphere, disk, ring, whatever you want, you can use. Next one is one of the axes must be passing through center of mass. After some practice, student will feel parallel axis theorem is a theorem where it will change axis to axis. We can take one axis and we can find moment of inertia about another parallel axis. No, it's not like we can take one axis. We can take one axis passing through center of mass and we can find moment of inertia about any other axis. We can find moment of inertia about any other axis. Clear? Point 3, both axes must be parallel. That's obvious because the word itself is parallel axis theorem. Now we go for the second theorem, perpendicular axis theorem. I'm taking a square plate, okay? And y-axis is like this, x-axis is like this, and obviously z will be like this. Observe this, x and y is in the plane, z is out of plane. X and y is in the plane, z is out of plane, okay? Then moment of inertia, ix plus iy must be equal to iz. This is perpendicular axis theorem. Okay. If you know x and y, you can find z. And the rule is very, very important. That is rule. X and y must be in the plane. Now let us go for the conditions or rules. Valid only for 2D objects. You can't use it for 3D objects. No. Second thing, all three axes must be perpendicular to each other and passing to the same point. And that point need not be center of mass. It can be anything. Yeah. In this diagram, it looks like sir, you did it through center of mass. Yes, I did it. Even you can take X, Y, Z axis like this. Still, you can use it there. Okay. Next one. That point need not be center of mass. Again, I reinforce on the same point. It need not be center of mass. Fourth one. X and Y axis must be in the plane of the object. That's the rule. Once you understand these rules, you can solve many problems. Now, this is a sense part. This is sense. When it comes down to formula, rule, law, something I can explain. Sense means I can't. Right? You should get this. So if you got this, it's your ability, not my ability. Now, my statement is like this. Suppose if I take a case here, I1, I2, I3. I1, I2, I3. All three are axes passing through diameter and in the plane of the disk. Disk or ring, you take whatever it is. My statement is moment of inertia I1, I2, I3 are same. I'm not using any law here. I'm not using any formula or something. If you want, I can derive it, but that's not the right way. By sense, I'm expecting. This is called a sense. By sense, you can say it is same. Ring is there and axis there. Now, if I take the system, if I move towards right like this, will the moment of inertia change? No. Now, what next? Observe, I'm rotating entire system. Means what? Including x also. Or I'm not rotating, just I'm turning my head like this. That also I can take. Okay. So if you look at this combination from this side, any orientation, whatever it is, about this axis, moment of inertia of this ring remains same, right? Now, if I rotate like this, then also it remains same. If I rotate like this, then also it remains same. So observe this, and are nothing but rotation of same axis, right? Pick up which axes are same in this. In this case, I1 equal to
I2.
I2, I3 also, because
Yes.
they are tangents, check it. Now I4 equal to
I5.
I5. Okay. Next, take this one, the next one. I1 equal to what? Tell me. I1 equal to
I2.
I2. I3 equal to
I4.
because you can see the logic, the symmetry, right? In this, tell me, I1 equal to
I2.
I2. I3 equal to
I4.
I4. So this is minimum sense. Like, sir, I can understand that I3, I4, the mass distribution is identical. So they are same. I2, I1, they are same. So you can write like this. I1 equal to I2. I3 equal to I4. Now this is sense, right? Now if you combine sense with theorem, it becomes a killing combination. See that? Let us take moment of inertia about an axis which is perpendicular to plane passing the center here. I can't indicate. Keep your pen or pencil on the screen like this, perpendicular screen at this point, okay? Once you place it here, you can see the z-axis, right? That is IZ, assume, IZ, right? Will you accept it? IZ is equal to, what the value, tell me? I1 plus I2? Will you accept this? Anyone is there who can tell me why I'm writing like this? IZ is equal to I1 plus I2? Perpendicular axis theorem.
Perpendicular.
Right. Now one more thing. I2 is equal to I1. So I write 2I1. Any problem? Okay. Now I take the same axis once again. I take I3 and I4. So IZ is equal to what the value? I3 plus I4, right? You know very well. I4 is equal to I3. So I write what, tell me? 2I3. Check it. If I take IZ is equal to I1, IZ is equal to I3, what I can conclude? I1 equal to I3. Observe carefully. I1 equal to I2, I1 equal to I1 equal to I3, I3 equal to I4 means what? All four are having same moment of inertia. Yes, by sense you can conclude I3, I4, I1, I2 are equal, but you can't conclude I2, I3 are equal. Yes or no? So sense plus mathematics, that theorems, will give you killing combination. So you can do well. Okay. Now observe question number 15. We have a disk here. Calculate moment of inertia of a disk about axis passing through its center of mass and in the plane of the disk. See, general thing is that, sir, let us integrate. But integrating is very, very lengthy. We take help of three things. First one is table that we have to mug up. Second thing is sense. Third one is theorem. By combining these three, we get the answer. Integration is very lengthy. You can't integrate for everything. Okay. Right. Disk. You know moment of inertia of a disk about an axis passing through its center perpendicular to plane. That is mr square by 2. You know that. Okay. About this axis, the dot indicates that, axis is perpendicular to the plane of the screen. Okay. Now what to do? Let us take the axis. This is the axis I want moment of inertia. Let us call it as Ix. And I'll take one more axis, that's Iy. Will you accept it? Ix must be equal to Iy? Yes, because sense, right? Common sense will say Ix equal to Iy. Will you accept it? Iz is equal to Ix plus Iy? You have to accept it. This is what, tell me.
Perpendicular.
Yeah. So last part, Iz you know very well, it is mr square by 2. That is equal to, instead of Iy, I take Ix because they're equal. So 2Ix. That implies what, tell me? Ix is equal to mr square by 4. Moment of inertia of a disk about an axis passing through its center in the plane of the disk will be mr square by 4. Go for question number 16. It is an extension of this question only. What is that? Calculate moment of inertia of a circular disk of mass m and radius r about an axis tangent to the plane. Means what? I need moment of inertia of an axis like this. Let us call this as I1. First of all, Ix equal to Iy. Iz is equal to Ix plus Iy. And we got what? Ix. Once you got Ix, you can find I1. Anyone is there who can tell me that what to use to get I1? Now parallel axis theorem. So I1 must be equal to ICM or I0. any symbol you want, you can use, plus md square. This is a parallel axis theorem. Now I apply that. That implies I1 is equal to, what is ICM? We just found it, mr square by 4 plus md square. D is what? The distance between two axes. That is r only. So moment of inertia of a disk about its tangent will be 5m r square by 4. That's the answer. So see the power of three things. That is, you have a list of formulas that is table. Second one is sense. Third one is theorems. By combining these three, you get a killing combination. Really, really high amount of power you get. You can solve moment of inertia of many, many objects. In question number 17, so the question is given to find moment of inertia about an axis. It's not a tangent, it's an axis. But what we know? We know square plate. No, we know rectangle, but we can convert into square, no problem at all, right? IZ, IX, IY. 1 minute. We know about IZ, right? What is IZ? Tell me. M A square plus B square by 12. This is the moment of inertia of a rectangular plate, but it is a square plate. So A equal to B. So you can write M A square plus A square is 2A square by 12 will be 6. So moment of inertia about IZ will be MA square by 6. Remember this. I know IZ, but I know this point also. IX and IY both are perpendicular to each other, and IX equal to IY. We already discussed it, right? So if you take that here, then observe carefully. This is IX, this is IY, right? Sense is enough to conclude IX equal to IY, right? Once you conclude Ix equal to Iy, you know perpendicular axis theorem, Ix plus Iy is equal to Iz, right? Iz is this axis, right? From the table, you know Iz. Now, once you know Ix equal to Iy, by using parallel axis theorem, you can reach I. This is the path. Sir, I'm not able to understand. Let us start with the table. First of all, table. Moment of inertia I is equal to m into a square plus b square by 12. This is the moment of inertia of a rectangular plate. But for square plate, what happens? Tell me. M a square by 6 because a equal to b. That is the moment of inertia about center and perpendicular to the plane. That means Iz. So this is Iz. Okay. Now, one more thing. This is from table. A little bit modification of table. Then Ix equal to Iy. This is by sense. Iz is equal to Ix plus Iy. This is by theorem. That implies m a square by 6 is equal to Ix plus Iy. But I can do one thing. I can replace Ix with Iy because they're equal here, right? So I can write like this. 2Iy. That implies Iy is equal to what? Tell me. M a square by 12. Clear? I know moment of inertia about y-axis, Iy. How to find moment of inertia about tangent? It's not exactly tangent, about this axis, I. Anyone is there? What to do right now? Use theorem. I is equal to I center of mass, I naught, plus md square. This is the theorem, parallel axis theorem. So I is equal to, I naught means moment of inertia about center of mass. We know moment of inertia about center of mass, Iy. Iy is passing through center of mass only. So it will be m a square by 12 plus m d square. What is d? This distance, right? This distance. What is the distance? This is diagonal. Diagonal is root 2a. Half of the diagonal, root 2a by 2, a by root 2. So a square by 2, right? Now if you simplify, that is equal to m a square by 2. If I take common, 1 by 6 plus 1, it will be 7 by 6, right? So finally, the required moment of inertia I is equal to 7 m a square by 12.